welcome to the workshop. So yeah, as I mentioned before, this is going to be like a very easy first time. So we're going to model a loop, and we're going to load it by a spherical system, and this is going to be at 3 Tesla. Then we're going to talk about the numerical domain, what it means, boundary conditions and materials, Lamport excitation, analysis setup. We're going to look at the results and look at the mesh. And I just skipped through this because I think it's easier if we like do it step by step. So first, let's do the modeling part. I mean, this is like very simple thing, and I guess the most you learn when you do it yourself. But I can like, or like if you have questions, you can ask me. Maybe Karthik has also some insights. But yeah, let's just try to draw a loop coil. The way I do it is I just like, can you see my mouse well? Maybe I should go slower, sorry. So I can either select it here on in this bar, draw a circle, and that draws me a sheet circle. And I can select it with the mouse, like how big I want it to be. And I can click on the circle if I want. And if I go here in the model tree, I can see the circle. And if I want, I can change the radius. It's in millimeters. So let's say we want a coil that's like 10 centimeters wide. So 100 millimeters. Now it's like too big for the screen, so I can go here, fit all.
Sorry to interrupt, but do you want to say like, okay, so what kind of solution, like driven model, and do you want to start off with the solution, or do you just want to start off with the modeling itself?
With the modeling, yeah.
Okay, all right.
It's gonna take me 5 minutes to do the whole model, so it's gonna be a very simple model. Can everyone see what I'm doing? Does it?
Yes, we can see.
Okay, so now I have this sphere, and now I want to cut out to make a loop coil. I will cut out. So let's say, oops, ellipse. I don't know what now. A circle here. Circle. And now I have these two circles, and I will just subtract one from the other, and then I can like select both of them, right click, and say edit, then Boolean, subtract. I want circle 2 is the tool part, and I subtract it from circle 1. That makes the coil. Then we need to make a port. And by doing that, I'm just going to draw a rectangle. Let's say we want a port here. Sorry, this is boring now, but like maybe best is if you do it by yourself, but I just want to give a short overview. So we make a rectangle. Then we can, I'm going to copy this rectangle. You see why later. I'm going to paste it here. Paste. So the first rectangle I use to subtract from the circle. Did anyone want to say something? So again, I'm right click. I do right click, edit, and then Boolean, and then subtract. So there's these different Boolean operations. One of them is subtract. I subtract. Now I need to pay attention. I need to the circle, not the two part. The rectangle, and I can switch it around like that. So now I cut out a hole for the circle. And actually, I made a mistake, I just realized. At first I need to select, maybe copy the circle and paste in here. Yeah, you need to figure this kind of out, these kind of tricks with the Boolean operations by yourself, but I'm still kind of confused by this, but in the end I figure out somehow how this works. Anyway, I need to make the port, and so I do edit again, Boolean, and here I need to intersect the circle with the rectangle to have the shape ready. So now this is the shape that I want for the port, but now the loop I need to subtract the rectangle from, and this is this rectangle. And I go again, edit, Boolean, subtract, and this is right now blank parts and tool parts. The rectangle is a tool part. Here we go, and now we have the coil is kind of ready, at least the modeling part. So now let's make the phantom, and this we're just gonna do a very simple spherical phantom. Maybe let's say head sized. So head, and again, like I can draw it in the modeling, but then if in the model tree, I can go and I can find the sphere. By default, it's assigned vacuum, so air. And I can change the radius, let's say, to 200 to 20 centimeters. Or actually, sorry, 10 centimeters. So the diameter is 200. It's about head size. Now we need to move it. There's two options. Either we can, again, do it in this window here, change the center position. So I'd like to move it along the Z direction by, let's say, 110. That's one option to do it. The other option is to, again, select it and right-click here, say Edit, and then Arrange, Move, and yeah, then you can move it. And in this little window here, you can see the X, the Y, the Z. Let's just move it by 1 millimeter just for fun. Yeah, so there's these two options, but it's best if you play around with this yourself. Now we see that for MRI, this won't work because now the coil is in the Z direction, and usually that's the direction of the bore. So let's just turn all of this. We can just like select all. I just hit Control A, so that selects all. But we can also separately with the mouse select each individual geometry. Now we can say again, edit, arrange, rotate. And we want to rotate it along the x-axis, let's say, by 90 degrees. Like that. And yeah, let's just keep it like that. So now we made the model. This is what we want to investigate. But because this is a numerical software and it works with equations, we need to limit the numerical domain. So because yeah, we have finite memory in the computer, we need to tell the software somehow where to finish computing, kind of. And we do that by drawing a circle, or like we do that by defining a numerical domain. Maybe for the guys of you that know FDTD, you guys know that it's rectangular, this numerical domain, but in HFSS, which uses finite element method, you can choose an arbitrary shape. So just to show you, we're gonna use a spherical numerical domain. So this is kind of an important thing. Right now we just did only modeling. So there we model the things that we want to investigate, but now we need to add something that's like unique to this software or unique to numerical computations. So we truncate kind of the numerical domain. This we do, we need to insert something by ourselves. In this case, I chose a sphere. You could also do a cylinder, you could do a rectangle, whatever you want. But I chose a sphere. And the distance to the antenna should be wavelength over 4. And at 3 Tesla, the wavelength is approximately, let's say, 3 meters, approximately. So lambda over 4 would be 3 over 4 meters. Let's approximate it to 1 meter. So this sphere, the numerical domain needs to be 1 meter away from the radiating element. So the radius of this sphere has to be 1 meter. Did it change? Oh, wait. So I did the wrong sphere. This is 100, and this sphere, the bigger sphere. So the first sphere here is the phantom. We're gonna give it a name. You can just like click on the tree, and you get this card of this sphere, and then you can just call it phantom. The second sphere, we can also give it the name numerical domain. Oh, I can't do space apparently. Good. It's a sphere that is, and then we can call this the coil, and we can call this the port. Just to be have a little better overview. Good. So we did that. Now, like, we only created kind of models, like 3D models. We did only with geometry so far, and we included this numerical domain, which we need to know. Like, it's a knowledge that we need to have, like, for this simulation software. But for now, it's only a 3D object, only like a modeling object. So for now, let's hide this numerical domain. I can right click, view, and we can say hide in all views. And let's deal for now only with our model. So let's give it like material parameters. So for the phantom, we can click on the phantom in the tree, and we can right click and then say assign material. And we can either choose from the materials that are given by default, or we can also give it our own material. And this we can do here by add material. And then this like menu pops up, and we could give it a relative permittivity and conductivity. And we can choose approximate parameters, let's say for brain tissue. I'm just going to guess relative permittivity of 50 and bulk conductivity of 0.5 Siemens per meter. This is how, for electromagnetic purposes, this is the only 2 parameters that matter. It's the permittivity and conductivity.
Don't you need to give it a density?
For SAR it matters, but not for the electromagnetic field.
Okay.
Maybe we can deal with it like in future sessions, but for now, because we're doing only electromagnetic fields, it doesn't really matter. So that was the phantom, and now let's work on the coil. And for now, this is a sheet. There's different options on how to do it, and maybe let's see how far we get. But let me just copy this whole design, and then we can later maybe explore other things, how to deal with that. Paste. Oh yeah, and in the project manager we can just define here HFSS, the name, workshop 1, and maybe I can make this model available with you. It seems to take some time. Yeah. And let's just call this test 1. Maybe we can come up with a better name later. So to come back to our model, let's hide this again. So right-click, View, Hide in all views. So let's go closer. So let's assign this coil. So for now, the computer doesn't know that, or the software doesn't know that it's a coil. So we need to tell it it's a coil. But we can do that by just like selecting it, right-click, assign boundary. And now we can. There's like different options. Sorry, different options how to do this. The simplest way is to say perfect electrical conductor, and that means that the conductivity is infinite. It's like a resistor with zero conductivity doesn't exist, but it's in the software, it's like quite common to do that. Let's just assign it perfect electrical conductor just for fun. And yeah, it also makes the computation a little faster, and then later we can maybe do a more sophisticated model of the coil conductivity. So that was the coil conductivity, and now we need to do the excitation. By the way, for me, it helps to look at this at the project manager tree. If you guys can see that where my mouse is. So if you work from top to bottom, first is through 3D components and model. So we kind of completed that part. Then circuit elements, we will talk about that later. And now we're working on the boundaries.
Boundary.
So we assign. Sorry.
I was on mute.
Okay. So the boundaries, we're working on that now. And so we assigned the boundary to the coil. So the second boundary is the numerical domain boundary. And so let me zoom out and let me make it visible again. View, show in all views. And now we need to say the simulation that we need to truncate the numerical domain with the sphere. So I need to select the surface of the sphere, and I can do that by just right-click in the model window. Say select modes, and right now I can only select objects. So if I select the sphere, it will select the whole sphere. But what I want is to select only the outer surface of the sphere. So again, I right-click, selection mode, and I can say faces. Faces means surface. And then now I click it, it looks the same, but now it's not the object, it's only the surface. So I selected it, now I can right-click, and I can say assign boundary, and we're gonna say radiation boundary. And what that means is that if there's any radiation coming from our coil, any radiation that won't be reflected, and that means that it's like in free space, as if there is no boundary. But because we are like in the simulation, we need to make a boundary, because he cannot do free space, because it would require infinite amount of memory. So this is kind of how we emulate a free space scenario. So now we can, oh, it actually didn't have assign boundary, radiation. Okay. One. Oh, okay. I'm doing the other model. So yeah, I'm not in test one. That was confusing. Sorry. Anyway, so we're in this. So this is test. No, doesn't matter. We're working on this design, and now we can see the perfect. So we were working on this like from top to bottom. Now we finished modeling. Now we're working on boundaries, and on the boundaries we can see that we have perfect E1. That's the perfect electrical conductor. It's the coil. Sorry, 10 seconds. I need to close my window. It's pretty loud from outside. Much better. So that's the perfect electrical boundary for the coil, and the radiative boundary, and we can see that is the outer layer of this sphere. And now working from top to bottom, we finish boundaries. Now let's go to excitation. So now we can have the port that we called earlier. Port. Let's zoom in on that. And again, we can do a right-click and say assign excitation. Then we can do lump port. That would excite this coil with a 50 ohm source. And yeah, as I said, it's a 50 ohm source. It's as if you have a generator and a 50 ohm resistance, and that you attach it to this coil. So then you need to give it an integration line. And it automatically, like if I move my mouse around, it finds like the center of the spot, and you need to give it a direction where he has to apply the voltage, and you want to apply it from the coil, between the two coil ends. So it's defined, finish, and we finish the excitation. Now, working from, again, looking at the project manager tree, we finish excitations because we want one coil, one excitation. You can see it. I'm going to hide the numerical domain again because it's confusing. But in the back of our minds, we know that it's there. Hide in all views. Fit all. So now we can apply local mesh, but we can maybe get into it maybe the next session, not now. And now we need to give the simulation software details on how we want him to analyze this problem. So we can go on analysis, right click, add solution setup. We can say I usually say advanced because I know I want him to do what I want him to do. And here we can see like kind of the basic thing what we want him to do. So frequency. In MR, usually we are only interested in a single frequency because it's a narrow bandwidth. And we can change it to megahertz, and 3 Tesla, it's like 123 megahertz approximately. Then we can say maximum number of passes, and this is unique to this finite element software, these passes. So there, he will start out with an initial mesh, and what a mesh is, we can look at later or very soon. And then he will refine this mesh to make your solution more exact. So this sounds abstract for now, but maybe it will become clearer later. So right now, let's set this to 1. So he will only use the initial mesh settings. this is not relevant. The rest is not relevant, except order of basis functions, but we can also talk about this later. Let's set it to 0 order for now. Then he goes into sweep, but we don't need this. This is only when you want to solve for multiple frequencies, and it automatically attaches, but we can just delete it for now because we need only one frequency. Okay, now we set up our problem, and now we can say analyze all, and it will solve the electromagnetic problem. This can take a while. But we can kind of observe how he's computing. Now he's doing like now he's actually computing, seems like. And it's finished. So that was pretty fast. And let's have a look at the results. So first thing, let's see the so again, as I mentioned before, in the project manager tree, we go from top to bottom. So we finished boundaries, excitation, mesh, analysis, we finished that. And then we solved it now. Solving, yeah, either you can do it here, right-click here, and say analyze all. You can also right-click here, say analyze all. There's like so many options. You can find your preferred one. So we solved it, and now we can, from top to bottom, we can look at the results. So we right-click here again, and we can say solution data at the very bottom. And this is, you can see the S matrix, or in this case, it's only S parameter because we have only one port. But this is the S parameter of this port here. So we can see that it's like quite reflective, and the angle is -7 degrees. So we can also look at the Z parameters if we want. So the impedance is 778 ohms, and the angle, so it's not purely real. There's an imaginary part, and the angle is -72. We can look at the mesh statistics, and for this initial mesh, the software decided to give this model 5,000 tetrahedrons. Yeah, and here we can look at statistics on like how long you used to solve it and stuff. For now, it's not interesting. So yeah, I'm just going to show you a different option of how to plot. We can also say generate of how to plot the S matrix. We can say, again, right-click on results, and say create module solution data report, say Smith chart, which is like a usual way of plotting S parameters. And it's already selected, Smith chart S11. And we can say click report, and we can see how S parameter is here. So yeah, obviously the call is not resonant, so we expect a high reflection coefficient, and that's how it is for now. Now let's have a look at the field. I'm going to go back to the model. And if we want to plot the fields, we need to select the surface where we want to plot the field. So in this case, let's just say the ZY plane, and the ZY plane will cut through the sphere. ZY, now it's selected, and we can say field overlays, right click, plot fields, and let's just plot the magnitude of the electromagnetic of the magnetic field. And yeah, 0 degrees, done. And we can see this is the field that is produced. You see, like this is like pretty messy, and the reason for that I will show you later. The reason for that is the mesh. So I'm going to hide, you guys can see the sphere, the phantom, we're going to hide it. View, hide in all views. So yeah, kind of, we can kind of see like qualitatively this makes sense because the sphere introduces a resonance. The coil produces some field and it decays with the distance to the coil. And yeah, it's like strongest in the sphere, in the phantom. Kind of makes sense, but it also looks kind of messy, and you wouldn't expect field bit to behave like this chaotic kind of. And the reason for that is the mesh. So now let's have a look. How does the mesh look like? Again, if you go on the screen, we can, if you see field overlays, we can either plot fields, but we can also plot mesh. So right click and say plot mesh. Oops, and I must select the geometry first. So let's try to select the same geometry, global XY. And I'm going to show you the mesh of this. Yeah. Let me hide this one. Visibility. So now we can see the mesh, and apparently this mesh is probably not fine enough. And you can also see that it's not very symmetric, and that may be the reason why the electromagnetic field is not symmetric. So the software, I don't want to really go into details of this, but finite element method discretizes the space, your problem, in tetrahedrons. And these, like triangles, they are only like in 2 dimensions, but actually they are 3 dimensional, but we can see that. These triangles discretize the space. And he chose like a setting, the simulation software right now, but apparently the setting is only an initial setting, and it's not fine enough. So we need to tell the software to make this mesh finer, so the solution will become more exact. And he can do that automatically actually. Can you guys still hear me?
Yes.
Okay. Originally we said until 45. Let me just, I think it is a good finish actually. Anyway, so this is like, we let the software run with one pass, and he created like an initial mesh that we can see here. And it's a good guess for like as a first mesh, but it's not good enough. And the way the mesh is like discretizing the space, the finer this mesh gets, the better the result will get. But at the same time, the finer this mesh gets, the more computer intensive it will be for the computer. So it can be that like I choose a 4 times finer mesh, but the computation time will be like 100 times longer because it doesn't scale linearly. Anyway, like it would take much longer. So he chooses an initial mesh that's like not too fine to have like a good approximation for the solution. And then in the following steps, he will discretize the space finer. Maybe one last look. We can actually, I'm also kind of interested in this. Like how did he discretize the coil itself? So I told you like these kind of triangles that you see, the tetrahedrons that are in 3 dimensions. So also on this on the coil there should be also some tetrahedrons. So let's see. Again, let's say so now I selected the coil, and I can say again field overlays and plot mesh. Last adaptive, and we can also see. Let me just hide this one here. Plot visibility. And that's the meshing of the coil itself. So this looks quite good, but apparently not fine enough. So yeah, at this stage, I think let's finish like the first part of this workshop. But what I wanted to show you is like we kind of I showed you what I wanted to show you. Let's say we did like the general workflow, and as I told you, like for me it's very helpful to work the way the software like kind of gives me the structure by this tree here, and we can go like from top to bottom. First you go to the model, so you are like modeling your problem. In our case, the three loop coil, and then you go down circuit elements. We can do it later in a future workshop. But then you do boundaries. That's necessary. So we did the perfect electrical boundary and the radiation boundary. So we understood the concept of numerical domain, and that we need to truncate the numerical domain. And in our case, we chose a sphere. So I need to zoom out. Yeah, but we can choose different. Maybe it can be the bore of the MR scanner. Then it will be cylindrical. But that's like our choice. And we did the excitation. We understood, in our case, we did like a lump port excitation. So basically, this is a 50 ohm source with a source with a 50 ohm impedance that's sitting here. So the coil is not matched right now, but we can match it later. Then we can give it like local mesh settings, which we haven't done, but we can do it later, like maybe next week or following week. And we set up an analysis. We set only with one pass, and it solved our problem. But as we saw, not good enough because the field doesn't look really symmetric as we would expect. All right, let me just show this. So yeah, it kind of makes sense, but kind of it looks kind of a little chaotic. So we need to work on this. We need to understand more of the passes, and then we also had a look at the meshes, also kind of which has to do, which is the reason why this field looks so chaotic. Okay, I think if we should take a break probably now for 10 minutes. And then, yeah, if you guys have questions, and also the guys who have problems with the licensing, then please log back in around at 3, and then we can probably go like one by one. So let's take a short break now and see you at 3. Is that okay?
Yes.
Sounds good.
Resume. I'm not sharing my screen. Share. So yeah, this is a good point, Karthik. So yeah, before analyze all, what you can do sometimes you're like if you have a more complex problem, and this problem like is our setup is not that complex. But if you have a more complex problem, what you should do or can do is right-click on your project and say validation check, and then he does check for any overlaps. He checks if you have like applied all boundaries and excitations and mesh operations, and if there's anything wrong with your setup, it will tell you this stage. Yeah, thanks, Karthik.
No issues. So I have one question, Jan. So right now I'm designing a birdcage, and the way I did it was I designed a loop and then I bent it and made 8 copies and attached them together. But when when I do a validation check, the 3D model, it gives errors. It says like, what is the error that I was getting? Something to do with like, you know, the shapes are not annealed properly or something like that. Like, so what would be your tip, like to design a birdcage? How would you design it?
How did you model it? Sorry.
So I tried two ways. Like one was, so I made the rungs separately, like rectangles. Then,
sorry, what again?
so I made the rungs of the birdcage separately. Like I made one rung, let's say, and then I made 8 copies of it.
Yeah.
And then then I made a circle for the end ring, and so the circle was like, I bent that circle. I made the end ring, instead of making it into a circle. What I did was I made a rectangle again with the required length, and then I bent it on a surface, and then added all of them. But when I do the addition, like before I go to simulate, it gives me errors.
Maybe you could send me the model.
Okay.
And then I could have a look at it. And if that doesn't work, I can think of a way. I can try to think of a way how I would model a birdcage.
Okay.
But I think the easiest is if you just send it to me per email. How big is it?
It should be pretty small. Like I can send the model to you over email. Yeah.
Okay.
Let me give it a try again. I'm working on an idea. Let me see if that works. If it doesn't, I'll send it to you definitely.
Mm-hmm. Yeah. Other people have questions or? If not.
So the exact error it says is non-manifold vertices found for part. So yeah, for the birdcage, so I added a bunch of, let's say, like a bunch of rectangles and like a circle and things like that. But it says non-manifold vertices found for the rectangle. That's kind of the exact error that it gives.
Non-manifold vertices. I have no idea what this means. Yeah,
yeah,
no,
I tried to heal the object, and like I was looking at the community wiki page and stuff like that, and tried a few things, but like it was not working. So, but like I'm trying a different idea. Yeah, if it doesn't work again, I'll definitely send you the model. Let's connect offline. Yeah.
I can maybe show you like the simplest way I would do it. Let me just like create a new insert new design. What I would do is I would take those kind of things here.
Yeah.
Oops. Yeah.
So it's not you're not creating a cylinder, right? You're creating a polyhedron, right?
Yeah. Sorry. A number of segments. Yeah. How many rounds do you want to have?
8. Let's say 8.
8. Okay. Let's say. Let's make it 64. And then you can, like, for example, you can just say select. I mean, I made 64 here, but you can make it like arbitrary.
Yeah.
You can say select object, select mode, select faces, and then you can start to select like the rungs that you want. And say edit surface.
Detach faces.
Yeah, I think so. Surface. Create object from face. That's what I would do. And then you have like, then you have these objects here.
Yeah.
And then you could make maybe a second one of these.
Mm-hmm.
Copy it, I guess. Edit, copy. Edit, paste.
Mm-hmm.
Then you have the second one, and that one I would just pick for the end ring. There the height is 1.2, so the start position And Z direction would be have to be 1.2, right?
Yeah.
Oh no, this was wrong. Oh, center position. Center position 1.2. But the what is it bigger?
I see what you're doing. Okay, yeah.
Actually, no, it's easier to just move it, eh? Let's delete this. Let's move this. Edit, arrange, move. Not arrange, but edit, duplicate along line. 0, 0, 0, and then 1.2, right?
Yeah.
So with numbers 2, then you can make this 8 0.2 or whatever, entering. Oh shit! Why does it do both? Anyway, then you would have to like make the entering also like that. But you know what I mean, eh?
Okay. Okay, I'll give it a shot. Yeah.
Can I undo? Yeah. I guess you would have to like create a separate one again, or make it a different. Yeah. Okay. Oh, that. This height segment 64 it was.
Yeah.
Yeah, and then you can just like select all of those. There's one way to do it.
Okay.
Just to make the entering, you know.
Sure. Yeah. Okay.
And that should work, I think.
You select all of the faces and do what? Like merge them or create another object from that face, right?
Yeah, you can create another object from it. Let's say edit surface, create object from face.
Yeah.
Then I would like delete those, but we can just hide them. Let's just hide them. But you would delete them. Hide in all views, and those you can select all of those.
Yeah.
And then you could, if you want, you can combine them or not.
Yeah, you can say Boolean add, right? Yeah, sure.
Yeah, now it's like one thing.
Okay,
and
cool.
That's how you can use the page. Yeah, that's how I would do it.
Awesome. Okay, thanks.
Yeah. Anyone has another question other than the licensing?
So Jan, I joined in late. If I'm not wrong, this is how to design a Birdcage coil, right?
Yes.
Yeah. So my question is, would there be a difference instead of like having the rectangular slots? So instead of the rectangular slots, we put on like a cylinder objects, 3D objects.
You mean for the Birdcage?
Yes.
Instead of having those conductors flat, have them cylindrical?
Yes.
Definitely there will be a difference, but the difference is negligible. Because this is like numerical software, and like here, I mean, it's good like if you can do it, but yeah, like how much like difference? It will be like not even a millimeter difference, right?
I was thinking in terms of like this Birdcage coil paper that Karthik had shared, where like they try to get different phases by having different excitations at different rounds.
What?
So to get like different modes of excitations on the Birdcage coil, like if you're putting like a 0-degree phase excitation on one rung and then another excitation on another,
Yeah.
that, like to get that, like would this work, or do we have to like stick to a more accurate model or something like that?
No, that I don't see why it shouldn't work. Like when you put the excitation, you drive one of them with a 0 phase, and the next one like you drive it with a 90-degree phase. You can do that in post processing.
Okay, all right.
That's the way I look at it. I don't. Yeah.
All right. Yeah. Makes sense, Karthik. Yeah.
Yeah. Anyone else has like questions? If not, then yeah, as I mentioned this in the beginning. I'm going to repeat it again, maybe, but also I think I'm still sharing my screen and I'm still recording. I'm going to stop recording now. Stop.